Uh, so welcome everybody to the seminar today, and we have Emil Martinec from Chicago. Will tell us about his about the Holar wind of black holes emitting brains. So over to you, Emil.
Thank you. Thank you for the invitation to speak. What I'd like to present today is some recent work that's in these two recent publications on the archive that has to do with what happens when when a black hole, a charged black hole, radiates its charge. So this is something that is believed through the weak gravity conjecture to be always possible. But I wanted to think about it in particular in the context of ADS-CFT in situations where not just ADS-CFT, more generally gauge gravity duality. So where one has some black hole that's dual to a non-gravitational system, where the non-gravitational system has a Coulomb branch to its configuration space. So that should be dual to some something on the black hole side of things and the gravity theory, where the charge constituents of the black hole can leak off and be radiated. So let me begin with an obligatory slide about the black hole information problem, something that's been with us for nearly 50 years now. It could be succinctly summarized with the question, what is wrong with this diagram? Right, the process where a black hole forms through gravitational collapse, undergoes some Hawking radiation, and then seemingly from the effective field theory point of view, the singularity disappears, the black hole disappears, and the question arises, how does the radiation contain the information about what formed the black hole? And we still don't really have a universally agreed upon answer to that question. But string theory is making strides in getting us closer. In particular, if we divide this problem into two steps, the first being, how does the black hole store the information about what fell into it as a sort of an initial question to be answered. And then the question becomes, how does that stored information get re-radiated through the Hawking process? So string theory has brought us closer to this resolution by giving us an accounting of near extremal black hole microstates through a non-gravitational system via the notion of gauge gravity duality. But because the gauge theory is strongly coupled and we don't understand the duality map very well, we still don't really understand what's going on at the horizon. So the paradigmatic example of that is the three-charged black hole made up of 1 brains, 5 brains, and momentum, where the brains are wrapping some 5 torus, of which we separate out 1 circle as being special, being the one that's wrapped by both sets of brains. And this is, in an appropriate decoupling limit is some non-gravitational gauge theory on the brains that's dual to some black hole geometry at strong coupling. And what we would dearly like to do is understand how this picture relates to this picture, but we're not there yet. Even more simply, we could talk about a class of systems where we wrap D brains on, say, a DP brain on a p-dimensional torus. And the geometry that is dual to that collection of brains is depicted on the slide here. And so let me just spend a little bit of time unpacking this geometry for those who aren't familiar with it. So the branes are charged under some antisymmetric tensor gauge field. If I have a brane with p spatial dimensions, it's a p+1 dimensional antisymmetric tensor gauge field. And it has a gauge flux, which according to the standard, sort of Coulomb law, should have a power law fall off going like 1 over r to the 7 minus p in 10 dimensions. And then the gauge field that's emitted by the brane back reacts on the geometry. And so we can locally solve the coupled system of equations of antisymmetric tensor gauge field strength coupled to Einstein gravity. And the back reacted metric looks like this, where in the directions perpendicular to the branes, if we work in polar coordinates, there's the standard angular spheres, and the gauge flux exerts pressure on the geometry, wanting to make the geometry, the angular spheres expand a little bit faster than you would see in flat space. And so that's encoded in this warp factor h to the 1/2, which as you get closer to the branes, makes the angular spheres decrease in size a little bit more slowly than r squared. Conversely, in directions along the p brane, there's the inverse of this warp factor, which means that the branes are exerting tension on the p-dimensional torus, causing it to shrink a little bit as you go in towards the source. Okay, and in addition, I've included some non-extremality. So this is a black DP brane, where the factor little f is the non-extremality of the geometry. And so when the radius approaches the horizon radius r0, time slows down, and the radial direction also gets warped. And if we're not dealing with D3 branes, there's also a warping of the string dilaton. So the string coupling constant is radially dependent. Okay. So just a few comments. For p equals 3, we have D3 branes in the near source limit is an example of the Maldacena gauge gravity duality, where the geometry is locally ADS 5 cross S5. Not the ADS 5 cross S5 that many people deal with these days, where the gauge theory is spatially compactified on a 3-sphere. Here we're compactifying the spatial dimensions on a 3 torus. And so there's a term in the gauge theory Lagrangian, which is something on the order of the radius, sorry, the curvature. So the curvatures, sorry, the gauge theory is n equals 4 super Yang-Mills that has 6 scalars that describe where the branes are in their transverse space. And those scalars in the Yang-Mills multiplet are minimally coupled. So there's a term that goes like r trace phi squared, where r is the curvature of the geometry. So if you have gauge theory on a sphere, the scalars are massive, and all the branes want to collapse into the center of ADS. But this term is absent if we have the gauge theory on a torus, because the torus is flat. And so the gauge theory has a Coulomb branch. And so you can put DP branes anywhere in their transverse space and get at least an approximate solution. It may not be static if the branes are excited, but in the extremal limit, where we turn off the non-extremality, the branes can sit anywhere. And this harmonic function that I wrote on the previous slide can be replaced by your favorite multi-center harmonic function. And the beauty of harmonic functions is that they have the principal linear superposition. And so, so if this is a solution, this is a solution. Okay. Yes.
Okay, so I have a question about the previous slide and the statements that you just made is this solution that you wrote down where the supergravity can be trusted, and so probably if you go far away, it is not trustable, or
So
from
if
the
you go
point.
far away, so this is a dimension dependent statement.
Dependent.
And so if P equals 3, so you have D3 branes, then the geometry is self-similar. It's ADS. It's just that it's ADS in Poincare coordinates, where the spatial slices are R3, and that R3 has been periodically identified to make T3. So that now you have gauge theory on T3. In the geometry, if I were to turn off this non-extremality, then what you would see is that as you send R to 0, the warp factor blows up. And so so H blows up, which means H inverse vanishes. And so you have a singular horizon at R equals 0 in the geometry. So there's some issues with what happens if you try to turn off the non-extremality. But if the which I'll discuss in a slide or two. But if you just say, I'm interested in the non-extremal system, then this non-extremality is causes the geometry at the horizon to be smooth. And then as you go out to R goes to infinity, it just becomes asymptotically ADS. For P less than 3, then what you have is a situation where the string coupling is getting weaker and weaker as you go out to large radius. And so eventually you stop trusting the geometry, basically because string theory becomes weak, the gauge theory becomes weakly coupled in the UV, which is dual to large radius in the bulk. And so for D2 branes or D1 branes or D0 branes, you have some kind of a bubble, of region where geometry is trustable, but that only persists out to some radius, and then beyond that radius, the theory is weakly coupled. But the standard spirit of gauge gravity duality is, you think of doing, having some decoupled gauge theory dynamics, which is dual to gravity. It's just that it's dual to gravity trustably only over a finite region. And outside that region, you just think of it, the UV is being governed by some kind of weakly coupled gauge theory dynamics. Does that answer your question?
Yes, yes. And typically, if for P less than 3, the cases that at high energy states would be described, would be outside of the purview of the supergravity, right?
That's right. So, well, so the picture would be that you have this black brane, it's got some, atmosphere of stuff around it. You can send in probes from the weakly coupled region and probe this black object. And those would be dual, those bulk operators are dual to standard single trace operators in the gauge theory, just as in the standard ADS case.
Right. Okay, thank you.
Okay. Right. But for any P less than or equal to 5, and going to the extremal limit, the dynamics, what happens is what I was saying before was that if we turn off the non-extremality here, and go towards R equal to 0, the geometry becomes singular in the DP brane duality frame. But as was observed by Banks, Fischler, Schenker, and Susskind a little bit before Maldacena, you can think of the system as being a realization of M theory in flat space, compactified on a P torus. So actually, the even near extremality, the system is not truly singular. that the brain dynamics knows how to desingularize the extremal horizon near R equals 0. But because the system has a Coulomb branch, as I was saying, where we replace the single center harmonic function by splitting the charge apart into several chunks. The black brain can radiate some of its charge as charged Hawking radiation. And that, as we'll see, is a highly suppressed process, exponentially suppressed, because the brains are heavy, and also, it's the entropy of the black brain is, n to some power, and so if you decrease n, you're decreasing the entropy, and so that will cause some further suppression. But for the decoupled gauge gravity system, this is really the only way the system can radiate. So if we think about, for instance, ADS5 and black D3 brains, all of the bulk gravity modes that are dual to single trace operators in the gauge theory that correspond to uncharged quanta, those quanta just live in bound states in ADS. Their radial wave functions die off like some power of the radius as you go out towards the ADS boundary. And so all the supergravity modes that are uncharged are confined. That's why we like to think about ADS. It's sort of gravity in a box. But the wrapped brains live in some kind of plane wave states in their center of mass, where they can radially escape off to infinity on their Coulomb branch. And so this provides a way of, without coupling onto flat space or introducing some additional perturbation to the Hamiltonian, which extracts energy from the system, this is a way of having a black brain that's under the purview of gauge gravity duality, but where there's a channel by which the black hole can decay. You just have to wait a long time because the process is highly suppressed, and so it's rare. Okay. So as the brain discharges and it loses energy, the geometry at the horizon shrinks as the radius of the horizon shrinks, and various things can happen. So for instance, if you've got you're compactified on a p-dimensional torus, if the radius of that torus as the brain evaporates gets smaller than the string scale, then the appropriate low energy dynamics doesn't take place on that torus. It takes place on the T-dual torus once the size of the torus gets less than the string scale. And so there's some, and that combined with various sorts of Gregory-Laflamme instabilities and other well-known phenomena in black hole physics allows you to map out a phase diagram of what happens as the system tries to cool down by radiating. And so depending on whether, what the dimension DP brain you're talking about, the phase diagram looks a little bit different. So for instance, for P equals 1, was proposed by Dijkgraaf, Verlinde, and Verlinde that in some regime of coupling and non-extremality, the system looks like what's called matrix string theory. And there's another regime near extremality, as I was saying before, where the dynamics approximates 11-dimensional dynamics in flat space compactified on an appropriate dual torus. Okay. And as you see for P equals 3, the system is symmetric in the coupling direction about some axis, which just reflects the S duality of n equals 4 super Yang-Mills.
Emil?
Yes.
Yeah. What happens is for P is equal to 0, is there no such diagram for the D0 brain? What is
No, there is. I just didn't draw it. It's just not two-dimensional. It's one-dimensional. So the structure for P equals 0 just looks like the following, that there's some regime where it looks like the BFS matrix model. So, 11D supergravity in some kind of light cone quantization. And then there's a place where there's a regime where it looks like black D0 brains. And then there's a regime where it looks like perturbative Yang-Mills quantum mechanics. And so if you started off with, this radius is something like n to the 1/9. And so for a given n, as you radiate away energy and you come down on this phase diagram, initially it looks like perturbative gauge theory leaking off radiation onto its Coulomb branch. As it gets a little bit cooler and has a few less D0 brains, it can start looking like a black D0 brain in 10-dimensional type 2A string theory. And then as you get very near extremality, there's this BFSS matrix model construction of M theory.
Mm-hmm. Okay.
So this was laid out in a series of papers I wrote with Vashi Sahakian quite a while ago now.
But one question here. So isn't that if you have large temperatures, shouldn't the BFSS should itself do a good job, because it's weakly coupled and the large energy regime, and so you have a very highly high temperature black hole.
So you have to ask, is the temperature too large for the BFSS interpretation of the dynamics to hold? So there you're trying to interpret the Yang-Mills Hamiltonian as being something like, P plus or P minus, I guess P minus, excuse me, of some light cone description of M theory, where N is like P plus. Mm-hmm. It's actually, P minus is, due to solving some constraints, is something like P transverse squared over 2n, something like that. So you're describing some object whose mass is like P plus, P minus, plus P transverse squared. And then just reinterpreting P minus as the Hamiltonian, solving some constraints. But the point being that the purview where the thing looks like objects in M theory is where their transverse excitation is of order 1 over n. So if the energy scale is sort of, how to say this? Let me back up a step. Maybe this will make it clearer. So remember, the dilaton is a function of radius in the system. So now let's just take P equals 0. Okay. And but in type 2A string theory, the dilaton controls the size of the 11th dimension. So as you come in radially towards the origin where the D0 brains are, that 11th dimension is getting bigger and bigger. Okay, and so below some radius, the system looks reliably like it's 11-dimensional. And so if the horizon scale is small enough, i.e. the energy is low enough, then it looks like you're looking at some object in a chunk of 11-dimensional flat space, as long as you're sort of well inside the sort of bubble radius that's set by the scale of the dilaton. If the horizon is bigger than that, then really you should be thinking of this as where, well, the 11th dimension is now smaller than the Planck scale, so I should really think about it as 2A string theory. And then I'm describing D0 branes in black D0 branes in 2A string theory. And then eventually you get out to a large enough radius that G squared n becomes small, and so perturbative, Atoft dynamics is the appropriate description of the dynamics, and that's the weakly coupled regime that I was drawing here.
Okay, I see now. Thanks.
Okay. So there's also a variant of this if you have intersecting D branes. And so the system I started the talk with, the D1, D5 system, is an example of that. We'll be talking about not the D1, D5 system, but its S-dual F1, NS5 system. And the reason for that is that there we have a well-developed perturbative worldsheet formalism for string theory in the presence of NS5 branes, where we can introduce the extra charge corresponding to a number of strings that wrap one of the circles of a T5 compactification. And in that duality frame, in the NS duality frame, the decoupling limit is to take the string coupling to 0 and the radius of this special circle to infinity. That's that extra circle, that what I call the Y circle, becomes the azimuthal direction of ADS3. The transverse R4 to the 5 branes consists of the radial direction, which becomes the radial direction of ADS3. Oops. And so that radial direction together with this azimuthal direction and time becomes ADS3. The S3, that's the angular sphere transverse to the 5 branes, becomes fixed size S3, and there's the remaining T4 that the 5 branes are wrapping, but the strings are transverse to. And this system is well known to have a continuum of what I would call Coulomb branch excitations, where you can, at finite cost and energy, take a string and pull it out to the ADS3 boundary. And you might think, gee, that sounds a little bit strange. Isn't the string becoming macroscopically big and very heavy? And the answer is no, that there's an electric H3 flux. So there's an H rho tau sigma, okay? And so the string is moving upward in time, so there's a tau dot, and it's wrapping the sigma direction, so there's a phi prime. And there's then a Lorentz force in the radial direction, which pushes the strings out, and that compensates the tension, and compensates it precisely such that it costs a finite amount of energy for strings to get out to the boundary. And those will be our Coulomb branch of F1 string excitations. And so in the worldsheet formalism, there are two kinds of observables, two kinds of probes. There are the ordinary supergravity probes, where I just look at some local operator that sends some supergravity mode into the middle of ADS and has it come out. But then there are also these long strings, and the long strings are traveling some time-like trajectory. And so it takes them an infinite amount of time to get out to the boundary of ADS. And so they have an S matrix. And it's that S matrix that we're interested in studying.
One question here. So in this calculation, the back reaction of the string on the geometry is ignored, right? And
that's right. So I'll be dealing with perturbative string theory. The back reaction, there are certain things that we'll take into account carefully. In particular, we'll take into account the Gauss law of these emitted strings. So for instance, the string winding on this circle is one of the background charges. And so across this string, the number N1 of fundamental strings changes by 1. And that's something in computing the Hawking radiation you need to take account of.
Okay. Okay.
But if you're asking, am I going to take account of the curvature that's sourced by this perturbative string, then the answer is no. That's something that typically in perturbative string you deal with perturbatively.
Okay. I see.
In some sense, what is built in is that you have a macroscopic number of these fundamental strings that are sort of dissolved into the background as this electric H flux. Okay, so in that sense, you're taking into account that back reaction of the macroscopic number of strings in the background. That you're taking into account exactly because you're talking about doing perturbative string theory in ADS3. And so that ADS3 is sourced by this electric H flux. Okay. So the usual description of the Hawking process proceeds by thinking about, one way of thinking about it is by thinking of pair creation of quanta near the horizon, some sort of vacuum fluctuations near the horizon, where one element of the vacuum fluctuation pair escapes to infinity as a Hawking quantum, leaving behind its antiparticle partner behind the horizon. And the usual Hawking paradox is that these vacuum fluctuations, being vacuum, have no structure, have no entropy or information content. And so you're radiating away things that have no information, carry away no information about the black hole. And once you've radiated enough of them, you notice that you're not radiating away any of the information about the black hole. And that leads you to the information paradox. And so, one nice way of thinking about this, which was investigated by Wilczek and students in the 90s, is to think about this process as a tunneling process where, say, I have a particle-antiparticle pair that fluctuates into existence near the horizon. And they wanted to ask the question, can I think of, this sounds very similar to the Schwinger process, where I have an electric field and there are vacuum fluctuations where a particle-antiparticle pair nucleates in that electric field. And if during the time in which they are allowed to exist by the uncertainty principle, if they can gain enough energy from the electric field that they can go on shell, then the charged particle can go this way, the anti-charged particle can go this way. And that's just sort of a tunneling process by which you take energy, vacuum energy, that's stored in the electric field, and you convert it into particle-antiparticle pairs, which slowly discharge the electric field, right? Because the back reaction, if you like, of the antiparticle electric field is discharging the background. So they wanted to ask the analogous question for Hawking radiation. Can I think of Hawking radiation as a tunneling process where the particle-antiparticle pair draw energy from the ambient gravitational field, allowing them to go on shell and become, real particles and that's what the Hawking radiation is. And so the answer is sort of. It's actually quite precise for the situation we'll be describing. And so to describe it, I want to think about the brains near the horizon and nucleating a brain-anti-brain pair. If you want to be concrete about it, the example we'll discuss a little bit later is this one where I have, this is a a picture of an ADS3 black hole where I have a string that's wrapping the horizon, and this depicts a string anti-string pair that's getting nucleated by the horizon, the string member of which is going to escape, and there's an anti-string that's trapped behind the horizon. And so we can, if we just dimensionally reduce this along the horizon, along the angular directions of the horizon, and just focus on the radial and time directions, we get some kind of effective center of mass dynamics, which has, standard covariant kinetic term, perhaps some mass, and a coupling to whatever gauge field the brain is charged under. Okay, and let's work in a metric, which I don't want to work in standard Schwarzschild coordinates because those are singular near the horizon. But you can work in any non-singular coordinate system where the radial component of the metric doesn't diverge as it does in Schwarzschild coordinates. So Eddington-Finkelstein is fine. Wilczek, Krauss, and Parikh worked in something called Penlevet-Gulfstrand coordinates, but anything really works. And then the next step in the analysis is to go to the Hamiltonian form of the path integral. So just do the standard Legendre transform from expressing the action in terms of velocities to expressing it in terms of momenta. And then the Hamiltonian becomes a constraint that enforces reparameterization invariance along the world volume of the brain. And so because it's a constraint, we can solve it for one of the dynamical variables, and let's choose to solve it for the radial canonical momentum. And then it turns out that, so the constraint is just quadratic in the momenta. So this is just solving some quadratic algebraic equation. And what you find is that the vanishing of the time components of the metric near the horizon implies that the radial momentum, when you solve the constraint, has a pole near the horizon. And the residue of that pole is entirely expressed in terms of geometric properties of the horizon. Kappa is the surface gravity. Omega is the angular velocity at the horizon conjugate to the angular momentum. And phi is the gauge potential at the horizon conjugate to the charge of the brain. And so what Parikh, Krauss, and Wilczek propose is that you then evaluate, so having solved the constraint h equals 0, the evaluation of the classical action. So what are we doing? I should have said. We're going to do some kind of WKB approximation to this tunneling process, where we say, okay, let's assume that a particle-antiparticle pair has been created near the horizon, and we're going to ask for the probability that the particle member of the pair tunnels across the horizon to become a Hawking quantum. And we're going to evaluate that tunneling amplitude in the WKB approximation. And that approximation is justified by the fact that the radial momentum has a pole. So it's getting really big at the horizon, and the WKB approximation is actually quite accurate. And so, well, it's a tunneling process, so the trajectory has to be somewhat non-classical to cross the horizon. So what Wilczek, Krauss, Parikh, et cetera, propose to do is to analytically continue the evaluation of the reduced action by deforming the contour of integration into the complex R plane to slightly avoid the singularity. So the idea is there's some pole at the horizon, and you want to do the integration from slightly inside the horizon to slightly outside, and you just deform the contour a little bit into the complex plane. And so using standard complex analysis, in the process, you pick up an imaginary part to the integral, which is basically half the residue. And so you get that the imaginary part of the classical action is the residue of the pole, a factor of 2, and then using the fact that, and a factor of pi from the Cauchy formula, and then using the fact that the temperature of the black hole is the surface gravity divided by 2 pi, you get this answer for the imaginary part of the action. Expressed completely in terms of geometrical properties of the horizon, the angular velocity, the chemical potential for charge, the temperature of the black hole, and then properties of the tunneling quantum, its energy, angular momentum, and charge. But then those quantities are conserved and enter the first law of black hole thermodynamics in precisely the way that the energy that's emitted by that's carried away by the particle decreases the mass of the black hole. And the angular momentum that's carried away decreases the angular momentum of the black hole, and the charge that's carried away decreases the charge of the black hole. And the expression then is this expression, minus it is the change in the corresponding properties of the black hole, which by the first law of black hole thermodynamics is just minus a half the change in the entropy of the black hole.
Just one question. So here, of course, you disregard the internal excitations, possible excitations of the brain itself, right? In this.
Yes, you could include those, and so a proper accounting for that would be to say that the imaginary part of the action will be this should really be minus a half the change in the entropy of the system. So if I have if I'm nucleating a string and I'm going to Hawking radiate a string, that string could have wiggles on it, and there's an entropy to those wiggles. And so in order to make those wiggles, you have to draw more energy from the black hole, and so you compensate the fact that the emission is suppressed the more and more energy in the quantum you're trying to emit, but you gain back a little bit because the quantum you're trying to emit has a density of states corresponding to the oscillations on the brain. So you could, in principle, include that. It's just that the lightest things that are the least suppressed are the things where the brain's unexcited.
Okay, unless the brain has some lot of zero modes or something.
Yeah, it has zero modes. For instance, one of the zero modes it has is angular momentum. So it can, you can radiate away the ADS. You can radiate away the angular momentum that's carried by the black hole, and things like that.
Okay.
Okay, so what Krauss, Parikh, and Wilczek found was a kind of a universal result for all black holes, that the emission amplitude is just exponentially suppressed in the change in the black hole entropy as a function of the various conserved charges. And while I've presented this as an amplitude for emitting charge quanta, it also applies to the emission of uncharged quanta. That in fact was the application that Wilczek and collaborators were interested in. It's just that you're sort of part of the emission of uncharged quanta carries down, in a spectrum that goes all the way down to zero energy. And when the energy gets to be of order the temperature, this suppression is order 1. And then you have to start worrying about what's the prefactor in order to get an accurate answer. And so that lies outside of its WKB analysis. You could do it as a higher orders in WKB. It's just I haven't done it here. So in order to, make my calculation reliable, I'm focusing on the situation where the branes are carrying some sort of extra charges which cause a substantial suppression. By the way, the same thing again occurs for uncharged Hawking quanta. If you ask that the Hawking quanta are not radiated in the S wave, partial wave, if it's radiated in some higher angular momentum partial wave, that causes this suppression to start being bigger than order 1, and the calculation gets to be more and more reliable. Anyway, one of the other things that these authors were interested in was answering the question that was asked somewhat earlier. Are you going to include the back reaction of the radiated quanta? And so they were interested in that question. In particular, they were interested in the question of what happens when the change in the entropy is not small. Then don't you get some sort of deviations from thermodynamic answers? The answer is yes. When delta S over S is not small, then what you need to do is incorporate the gravitational back reaction. You want to solve the gravitational. So what we did in our analysis was we solved the world line or world sheet or world volume constraints of the first quantized action. But in principle, you could couple this world line dynamics to the ambient gravitational theory, in which case the energy and other charges of the emitted quanta couple to the corresponding charges of the black hole directly through the gravitational constraints and gauge constraints. And so in this regime, these folks did a somewhat more sophisticated analysis where they also solved the space-time field theory constraints and found again that this is the answer, that even when the change in the entropy is not small, the leading order probability of emission is just given by the change in the entropy of the black hole. Just so I pace myself, which I'm terrible at. I have about half of my slides remaining, so I can either skip some sections or I can proceed at the same leisurely pace I've been doing and run over time.
Yeah, we can, of course, go a little bit over time, like 15 minutes or something. Then we, because otherwise we won't
Okay,
have.
yeah, that should be plenty. All right. So let me just say a few words in detail. The calculation that I've described is quite straightforward and quite pretty to see unfold, where you just solve the Hamiltonian constraint and out pops all these geometrical properties of the black hole. It's quite amusing to see happen. And the place where I first encountered it in what I was thinking about was the ADS3 example, where we have ADS3 made by fundamental strings and NS5 branes. And there, you can be quite precise about what's going on, because the world sheet dynamics of the strings in the background of an ADS3, or also known as a BTZ black hole, is just given by group theory. Locally, the geometry is just that of the SL2R group manifold. That's what ADS3 is. And the electric antisymmetric tensor field strength is just the covariantly constant volume form in SL2R. And of course, the black hole is not global ADS3, it's a black hole. And the way it's realized is through a quotient of global ADS3. That is, if you identify global ADS3 by a discrete left and right multiplication, this discrete identification generates a non-compact discrete group. The identification of global ADS3 by that group Z, which is just Z, yields the BTZ geometry, where in this expression, R plus and R minus are the outer and inner horizon radii. The most general BTZ black hole carries ADS3 angular momentum, and so it has both an outer horizon, which I've depicted in blue, and an inner horizon, which I've depicted in pink. And so it has an asymptotic ADS3 region. The black hole singularity is inside the inner horizon. And of course, the maximally extended crustal geometry has two asymptotic regions to it. Okay, and so if we look at classical motions, they're just geodesics in this group manifold, which we can get by solving the Hamiltonian constraint. And so those come in various flavors: time-like, null, and space-like. If you take the space-like geodesics, so those can either emerge from the singularity, pop through the past horizon, and escape to asymptotic infinity, or they can bounce from one asymptotic region to the other. And there's an operation called spectral flow, which is this operation in the SL2 current algebra theory, where you left and right multiply an SL2Z, SL2R Wessamino-Witten model field by a function of Z on the left and a function of Z bar on the right. And so if you had something which was a point-like motion, some geodesic, this transforms it into something which is not just a point-like thing, but something which has spatial extent, because it now depends on the worldsheet spatial coordinate. And it turns out that it's actually what you generate by this operation is a string that's winding the azimuthal direction and going out to the asymptotic boundary. And so if you start from the space-like geodesic, so if you start from, say, if you start from this trajectory, okay, and you make this transformation, it becomes this time-like trajectory of a winding string. And the energy and the angular momentum of that winding string is just determined by the group theory of the SL2R Wessamino-Witten model. And so the process we're interested in is one where we have two classical trajectories, one which represents a string outside the horizon on one of these winding trajectories running off to a time-like infinity, and then an anti-string, which is just a corresponding trajectory running backwards in time, and then a non-classical segment where the anti-string tunnels across to become the string that escapes to infinity. And so running through this evaluation of the classical action of the string with the imaginary part of its action that comes from the tunneling, you reproduce the answer that I gave a few slides ago, that the change in the entropy is it gives the tunneling amplitude. And okay, well, the energy of the black hole is given in terms of the horizon radii by standard expression. The angular momentum of the black hole is also determined in terms of the horizon radii. And the entropy that you get from what's essentially the Carty formula for the dual CFT2 is just the product of one brane and 5 brane charges times the outer horizon radius. And so the emission of a string is suppressed by the fact that when you emit a string, you're changing n1 by 1. And so this capital N becomes smaller by n5. And so the change in the entropy becomes smaller by a factor of n5 times the number of windings you removed and a factor of r plus, the outer horizon radius. And so for big ADS3 black holes, this emission is indeed heavily suppressed. Even if you only wind once, things are suppressed by the number of 5 branes in the background, and the bigger the BTZ black hole gets, the more suppressed its emission, the string emission is. Okay, so I'd like to now give an interpretation of this result. Oh, I should say, to get this answer from the worldsheet calculation of the imaginary part of the action, involves some actually rather amusing features of black hole thermodynamics, because the radius of ADS3, the ADS3 cosmological constant, is basically n1, n5, up to some factors of 2. And so because you're thinking about a process in which you're changing the value of n1, n5 of the black hole you're leaving behind, you have to be working in an ensemble for the black hole in which the ADS3 cosmological constant is a thermodynamic variable. And you only get the right answer by incorporating a chemical potential for the cosmological constant and treating it as a fluctuating thermodynamic variable. That's where, in fact, this term comes from, by and large. Okay. So let's interpret this result that seems to be quite universal, that the change in that the emission probability from a black hole is just the change in its entropy. It's basically telling us that the probability of emitting stuff from a black hole is entirely determined by phase space, by the fact that the black hole has an huge internal density of states, and that stuff, when it falls in, gets lost in this huge internal phase space and has a hard time finding its way back out. And the way to quantify that is to say, well, what are we computing? When we're not specifying which microstate of the black hole we end up with, or which one we started with. And so even if the black hole was initially in some pure state, then we haven't specified which final state it's making a transition into. And so we should do, the thing that we're computing is really an inclusive process where we don't specify the final state, we just sum over final states. And how many final states are there? There are e to the s final of them. And so that explains this piece of the transition probability. The other piece of the transition probability is that, when you're computing an inclusive decay process, you sum over final states, the matrix element for the transition for each possible final state. And what this calculation is telling you is that the matrix elements for any one of these transitions is approximately e to the minus s initial over 2. And that should ring a bell, because in the eigenstate thermalization hypothesis, that is basically saying, what are the sort of generic thermodynamical properties of highly excited chaotic systems, which is what we now understand black holes to be, that matrix elements between energy eigenstates of simple observables are given by the VEV of those observables in individual eigenstates, and then some off-diagonal matrix elements, which are characteristically of order e to the minus the entropy over 2 times some smooth factors of the energies of the two states, and some typically random matrix, or what can be approximated for many purposes by a random matrix. And what we've computed is something which is essentially the same thing. We're not working in energy eigenstates of the entire system. To the extent that we can approximate the system as there being an inside of the black hole and an outside, what's happening is that the black hole is making a transition where between one black hole, the initial black hole, and a final black hole, and in the process emitting a Hawking quantum into the environment. And so I'd like to model that by saying that if we just focus on the black hole part of the system, that the black hole is making a transition. And the interaction Hamiltonian has matrix elements which are of order e to the minus s of the initial energy over 2 times some random matrix. And that if we then took that amplitude, squared it, and summed over states, that we would reproduce the answer that we got. Sorry, there was a question?
Yeah, this RFI which you wrote down, this random matrix parts, what is the proposal? Is it a GUE or it's from?
I'm not specifying at the moment which ensemble it's drawn from. That will depend on the details of, but I would imagine probably something like a GUE, simply because we're dealing with charged systems, and so. But that's something I really want to specify at the moment, which ensemble I'm drawing this from. And I don't really particularly care in the calculation that I'm outlining here. The only way that enters is that when I square this matrix element and sum over states, that I'm just going to reproduce the variance of this thing, which is order 1. And that will be true for any of the ensembles that you might want to consider. I should also mention that this ansatz is consistent with the adjoint process, right? So if I interchange the roles of the initial and the final state, swapping them, then I'm talking about the thing I'm calculating here is something where I start with a slightly larger black hole, making a transition to a slightly smaller black hole, and then in the process emitting a Hawking quantum. But I could also talk about the process where I start with a slightly smaller black hole and go to a slightly larger black hole by absorbing an exterior quantum. And that will be governed by the adjoint matrix element, which just interchanges the roles of the initial and final states. And so the suppression here will now be by e to the minus s final over 2. But then when I square that and I sum over final states, the matrix element just cancels against the density of states. And not surprisingly, the corresponding absorption amplitude is order 1, which is what you would expect. And in the WKB calculation that I sketched earlier is just the statement that when I'm solving this constraint, there are 2 solutions, one corresponding to radially outgoing quanta, and one corresponding to radially ingoing quanta. The radially outgoing one is the one that has a pole because I have to tunnel outside the horizon. The radially ingoing one has no pole. And that's because there's just some classical evolution across the horizon for ingoing things. So this ansatz is consistent with that feature.
Can I also ask something? This particular phase that you mentioned, right? This is typically what you get as the phase for the outgoings, or even for a scalar field. That is for the outgoing mode. That will be the phase near the horizon, right?
Yes. So one thing I haven't evaluated here is that I've just focused on the very near horizon part of the dynamics, where I've created this quantum, and I ask, for the particle, or sorry, the string to start at R naught minus epsilon, and then tunnel to R naught plus epsilon. There's of course a whole nother classical part of the dynamics, which is asking for that Hawking quantum to escape the near horizon region and get out to infinity. And that's a whole classical evolution. And in fact, it need not get out to infinity. There will be some amplitude for it to be reflected back into the black hole. And that's the province of what are called gray body factors, which I've not discussed here, but which are certainly part of the dynamics. So, once created, some fraction, well, in fact, for the uncharged quanta in ADS 3, none of them get out, right? They reach some finite radius and then bounce back in. So that's all classical dynamics, which I haven't been discussing. But yes, that's part of the story. Okay, so the picture that sort of arrived at is that in the quantum theory, the transition matrix elements are pretty much entirely governed by the phase space volume of the black hole. And so in the classical limit, that's infinite because the entropy is proportional to 1 over h bar. And so the phase space volume goes to infinity in the classical limit, and you toss something in, and it just sits there ergodically exploring this infinite dimensional phase space, and its probability to come back out is 0. And of course, black holes have 0 temperature in the classical limit. And so you should, the cartoon I have of the black hole now is just that it's this thing which is sort of much bigger on the inside than it is on the outside. There's sort of this enormous phase space volume on the inside. And if you take a snapshot of the black hole at any fixed time, there's a tiny part of the phase space, which is, Hawking quanta just outside the black hole. And, small amounts of the quantum probability distribution leak out into that, that order h bar piece of the phase space, and then can escape to infinity. But you shouldn't think of the quantum horizon as any kind of causal barrier. It's really, its causal properties really here are a consequence of notions of phase space volume and ergodicity. And of course, then the first question one should ask is well, what, how is that possible? How can stuff be at the horizon? And my answer to that, because I am sympathetic to the fuzzball program, is the fuzzball idea that you should really ask how much of this classical Penrose diagram is trustworthy. And of course, the part of it which is sort of down here is a fiction. As I've emphasized in this ADS3 example, the strings are in some kind of S matrix where they collapse into the five branes to make the ADS3 black hole, and then they Hawking radiate to infinity. And the whole Hawking conundrum is that naively, classically, the strings that collapse to make the black hole are over here, and the strings that are Hawking radiating are over here, and these are space-like separated. And so how can any of the information about what you threw in make it into the Hawking radiation? But if instead the wave function of those strings persists out to the horizon scale, and it's just, there's some interior which is some plasma of strings, but which has some finite probability for its wave function to live at the horizon. It's just exponentially small amount of it that is living here at any given time. Then that's basically what the calculation is telling you, is that there's a finite probability to find those strings near the horizon, and their escaping is just the amplitude for them to find themselves in a very rare part of the phase space where they can escape. Sort of equivalent to the question of, what's the amplitude for all of the air molecules in the room to all of a sudden find themselves in the corner. That's a very unlikely process, but there's a finite amplitude for it to happen. And on the rare occasions where it does happen, you can, pluck a large number of particles from the corner of the room. And that's the sort of process that we've been calculating. So the conclusion that I would favor is that instead of the process we calculated being something where a particle, a string, anti-string pair were created near the horizon and one member tunneled out and the other member is sitting just inside the horizon, is that instead what we really have is some kind of soup of branes that's in a non-geometrical phase, where they're sort of n-squared deconfined brane degrees of freedom, similar to the weak coupling picture, where the gauge theory is just in some kind of deconfined phase. That's what the Hawking-Page transition is, where black holes form in the gauge theory is a deconfinement transition. And so that they're sort of order n squared or order n in the ADS3 context, degrees of freedom that are in that non-geometrical phase, but only n to the 0 of them are describing geometrical quanta in the vicinity of the horizon. And so if the strings that are being radiated are governed by the calculation that I did, it's simply that the amplitude for pulling a coherent brane to be radiated onto the Coulomb branch from this plasma of branes is governed by the calculation that I did. Because I really only used the part of it where this quantum tunnels out from the vicinity of the horizon. I didn't really use any of this at all. And so there's no reason to postulate that it exists. So to summarize, the Hawking radiation of charge from a charged black hole is a rare event, but in these decoupling limits that have been of interest for the last many years of gauge gravity duality, can be the dominant decay channel. And that emission probability of these charge quanta is governed by the change in the black hole entropy in a manner that's consistent with ideas of highly excited chaotic systems that we've come to accept. And a simple microscopic explanation for the dynamics is that the interior of the black hole is in some non-geometrical phase, and that these charged quanta are emerging from that non-geometrical phase onto the Coulomb branch in a way that's very reminiscent of what happens at weak coupling, where the way that black DP brane system decays at weak coupling is that all of the strings that are binding an individual brain from the rest of the ensemble, that the off diagonal matrix elements, which are stretched strings, all manage to decay all at once, allowing this one DP brane to escape. That's the weak coupling picture. And I'm arguing that something very similar to that is happening in strong coupling. So thank you.
Thanks for this wonderful talk. So we should have questions. Okay, let me ask then. So the claim is somehow that the semi-classical geometry itself is sees an average the average process. So I think that you would explain it, that would agree that the semi-classical geometry captures average features of this emission process.
Yes, that's something that I think is a kind of a theme in recent investigations, that gravity is not sensitive to microphysics, that it's computing some sort of average quantity. I don't necessarily want to subscribe to the whole replica wormhole island story, but it certainly does seem that that gravity just doesn't have the resolution to that would be required for you to compute some kind of exclusive decay process. Gravity would have to have some energy resolution of order e to the minus s for you to sort of isolate a very particular microstate and say, that's what I'm making a transition into. That just seems to be beyond its capabilities.
Okay. So it is known that if you have, say, non-extremal black holes, the near horizon geometry has this instability, right? This instability towards fragmentation, and so how does do you think that can play a role in this? Whether it can be also a way to see the fuzzball story, that the fragmentation gives you some kind of a local.
I'm sorry, what sort of fragmentation are you thinking of?
This Brill instant on like fragmentations.
So that I think is an example of the sort of thing I was talking about. So indeed, in the early days of ADS-CFT, there was a very nice paper by Michelson, Moore, and Strominger. Michelson, Maldacena, and Strominger, excuse me, where they looked at the ADS2 example and used this Brill instanton to compute the probability for an ADS2 black hole that's carrying some of the brain charges of string theory to fragment into multiple ADS2 black holes. So that's, I would say, that's an example of the sort of process I was computing, where their answer for the using this Brill instanton was that the amplitude for this fragmentation to occur was exponentially suppressed in the change in the entropy between the initial black hole and the final multi-black hole state. So So yes, if you like, the same thing would have occurred for me if I would have asked the question, not for me to radiate strings from my D1, my F1 NS5 system, but couldn't I also radiate NS5 brains? And so couldn't my BTZ black hole break up into multiple BTZ black holes by the 5 brains going onto their Coulomb branch in addition to the strings going onto their Coulomb branch? So I could take, N1, N5 and partition it into 2 pieces, N1 prime and N1 double prime, and N5 prime and N5 double prime. And I could ask, what's the amplitude for my BTZ black hole near extremality to fragment into 2 BTZ black holes? There's a finite amplitude for that to happen, and it's governed by the exponential and the change in the entropy, because the entropy by the Carty formula is something like e to the square root of N1, N5. And if I take my initial N1, N5 and split it off into N1 prime, N5 prime, and N1 double prime, N5 double prime, that's a hugely smaller entropy for the final state than the initial state. So that's why this process is hugely suppressed. But I don't believe it's suppressed by anything more than that. It's purely that the reduction in the phase space, the size of the phase space between the initial configuration and the final configuration. And the same thing will be true for JT gravity in ADS2 black holes. This Michelson-Maldacena-Strominger calculation is saying that same thing is true there.
Okay, so if one has this picture that suppose the fragmentation is due to this emission process, as you were saying, and similar to the emission process, and then you have created some kind of a fragmented background after this. So now, if you think about a emission in this fragmented background, a further emission, and how it will look, it will also, one can probably do it from individual throats, or it's or somehow there will be contribution that one has to take into account in a different way, or
yeah. So well, usually one thinks of the emission happening in some sort of S wave. At some point, the brains, the Michelson-Maldacena-Strominger calculation was basically that you use the Brill instanton in ADS2, and then you work with some kind of S wave and some kind of angular S2 or something like that. But really, when the brains get far enough from each other, they're living in some kind of environment of supergravity. And so at some point they're going to decohere, and you're going to notice that they're actually not living in some S wave, but you find that the black hole is somewhere on the angular 2-sphere. And so the sort of picture of ADS2 fragmentation and multiple throats and so on is that it's that once they've sort of gotten far enough apart from each other and the wave functions decohered a little bit, I can say that, yeah, there's this throat here on, this part of the angular 2-sphere, and then there's, some distance away, something on some other part of the angular 2-sphere. They're all sort of flying apart from each other in different directions. And, overall, it's some kind of S wave, but, after the thing's decohered, any piece of the wave function is going to look like some, decohered thing with a bunch of throats. And so that, I think, is the picture. You sort of, things are in an S wave and then in some kind of very near horizon region, but once things get far enough apart, you start seeing that it has multiple throats.
Yeah. So my question is, some can one take into account? So this calculation that you gave is like a unfragmented near horizon geometry. If one looks into an emission from a fragmented near horizon geometry, is this going to be a very different, or I mean, you
I
also,
don't think so. It's sort of just, I think, orders of, it depends on what approximations you want to make. So for instance, what I just said would apply, I think, to the string emission that I calculated,
Mhm.
where the string being emitted is in an S wave on the S3. And so the question is, to what extent should I think of that emitted string as being some really heavy semi-classical object, which at some point interacts with its environment and decoheres, or how long should I think of it as persisting in some kind of pure S wave state where it's totally delocalized on the S3? A
Yeah.
perturbative string theory calculation of the sort that I was doing would just say, okay, it's, I've got some S3WZW, some SU2WZW model, which is describing the S3. And I'm just, going to put the radiated string into some kind of S wave, lowest angular harmonic in the S3WZW model.
So you can basically incoherently add up the emission from each of the introdes individually, and that's the idea, and then patch it up some. Yeah, okay. I see. Okay, so yeah, thanks for this nice talk again. And so I close the recording.